Section 2.1 starts to get at this concept that is fundamental to precalculus study, and that is the concept of a function. What a function is simply stating that each input has, at most, one output. I like to think about it like this, kind of visually. If I've got this machine, and I'm going to call it the f of x machine. If I stick the number 5 into the machine, that's my input, my output might be something like 2. If I stick the number -4 into the machine, my output might be something like -7. And then if I come back and try and stick the number 5 into the function machine again, it should give me out the exact same thing I got out last time. It should give me out a 5 again. That's the idea of a function, is different numbers go in and come out with different outputs, or maybe the same output. But when we put the same number in twice, we get the same output both times. A little bit of vocabulary around functions that we use. First is the domain, is the list of all of the possible inputs. Those are the things that are going into the machine. Over here, that's what goes into the machine. This is the domain, things that go in. Usually the inputs we represent with the variable x, what actually goes into the function. Contrast this with the range, that's the outputs. Often we use the letter y, that's the stuff coming out the other end. This is the range of the function. So domain and range, inputs and outputs. And then special type of functions are called one-to-one functions. And that simply means that each output spell output, right? Each output has at most one input. In other words, if I get 5 as an answer, I'll never get 5 as an answer again unless I use the same input. And we'll get more to that idea later along in the chapter. A couple things we want to be able to do with the function. The first we want to be able to do is evaluate the function. We'll see some notation here that looks something like f of x equals 2x squared minus 4x plus 3. And it's important to note here that f of x on the left side there, that is not f times x. That is a notation that names the function f and has x as inputs into the function. So we're never going to solve for x by dividing by f. We don't do stuff like that. It names the function and tells us what variables are in the function. Essentially, this is saying f of some stuff is equal to 2 times the stuff squared minus 4 times the stuff plus 3. And we're going to simply fill in the stuff. So as an example, using this f of x function, let's find f of -3. This means we're going to take -3 and replace the x's with -3. So we have 2 times -3 squared minus 4 times -3 plus 3. Order of operations tells us to evaluate the exponents first. -3 squared is 9, minus 4 times -3 plus 3. And then we can multiply. 2 times 9 is 18. -4 times -3 is plus 12, plus another 3. When we add that together, we're going to get 33. So we say that f of -3 is equal to 33. In other words, when negative 3 goes into the function, 33 comes out. Let's try another example. It's a little bit more involved, though. We're going to do f of a plus 2. And just by way of reminder, because it's not on my screen, you probably already have this in your notes, though. F of x is 2x squared minus 4x plus 3. So this time we've got this a plus 2 inside the function, so that's what's going to replace the variables. We have 2 times the stuff squared. In this case, the stuff is a plus 2. Minus 4 times the stuff. In this case, a plus 2. Plus 3. Simplifying is going to be essentially identical. First we have to square the binomial. So we square the first term, and then we have the product 2a plus 2a is 4a. Plus 2 squared is 4. Minus 4 times a plus 2 plus 3. Distribute through parentheses gives us 2a squared plus a plus 8. More distributing, negative 4a minus 8 plus 3. Combine like terms, there's only 2a squareds. 8a minus 4a is 4a. 8 minus 8 plus 3 is a positive 3. And we have our final solution, 2a squared plus 4a plus 3. We're simply replacing the variables, the x's, with what stuff goes into the function. So let's look at another one. What number was that? 2? We're on 3 now. Let's find f of x minus 1. And again, it's off my screen. So just as a reminder, we had f of x was equal to 2x squared minus 4x plus 3. So in this case, we're going to take x minus 1 and replace each of the x's. So we have 2 times stuff squared. In this case, it's x minus 1. Minus 4 times stuff, which is the input of x minus 1, plus 3. It's okay that we use the same variable. We're still replacing the x's with whatever the stuff is. Squaring then first, that's order of operations, gives us x squared minus 2x plus 1, minus 4 times x minus 1 plus 3. Distributing through parentheses, that's 2x squared minus 4x plus 2, minus 4x plus 4, plus another 3. Combine like terms on the 2x squared. We've got negative 4x, and negative 4x is negative 8x. And 2 plus 4 plus 3 is 9. Let's do one last of these. Let's find f of x plus h. We can also have several variables going on. And again, the function we said we were talking about was f of x equals 2x squared minus 4x plus 3. And so again, we're going to take the x plus h, and it's going to go into each of the x's. So we have 2 times stuff squared. That stuff is x plus h. Minus 4 times stuff. That stuff is x plus h plus 3. And in much the same way as the previous two problems, we'll simplify using the order of operations, doing exponents first. That's x squared plus 2xh plus h squared minus 4 times x plus h plus 3. Distribute through parentheses, that's 2x squared plus 4xh plus 2h squared minus 4x minus 4h plus 3. And in this particular problem, there really are no like terms. So it's big, it's ugly, but it's right. That is what f of x plus h is going to equal. And we can do all sorts of problems like this, picking any type of function and picking any type of input, number, variable, expression, and just simplify it out. In fact, on the homework assignment, you get a chance to do a lot of that. But I want to look at one special thing that we can do with functions that's going to come up a lot as we continue with our study of math, particularly when you get to calculus, is calculating this thing called the difference quotient. Or the average rate of change between 2 points. I'm going to set this up with a graph. Here's the graph. And I'm going to pick 2 points, one over here on the left and one over here on the right. And to find the average change between those points, we would connect the dots. Now this first point has an x-coordinate of x, and if we plug that into the function, it'll give us f of x for an output. So at x, it has a height of f of x. The second point over here, we're going to say moves over a distance of h. So if we move over a distance of h, that's going to be x plus h for the first coordinate, comma f of x plus h for the height. And we know that to calculate the slope between 2 points, that's going to be y2 minus y1 over x2 minus x1. In this case, y2 is f of x plus h, minus y1 is f of x. And this is all over x2, which is x plus h, minus x1, which is just x. And that's kind of nice because x minus x goes away, and so we end up with the slope of f of x plus h minus f of x all over h. This thing is called the difference quotient. It calculates the average rate of change between 2 points. So let's see if we can find a difference quotient with an example. Let's do f of x equals 3x squared plus 2x. And we're going to find that difference quotient. Well, for the first part, f of x plus h, we're going to stick x plus h in for the x's. So we've got 3 times x plus h squared plus 2 times x plus h. Next part is we're going to subtract the entire f of x. So we will subtract in parentheses, this is important, when we subtract, we need parentheses, 3x squared plus 2x. And this is all over h. Order of operations is going to have us do the exponent first, so that's going to be x squared plus 2xh plus h squared plus 2 times x plus h minus 3x squared plus 2x in parentheses for that last bit. And that's going to be important because now we're going to distribute through parentheses. Oops, I forgot the denominator, didn't I? It's all over h. As we distribute through the parentheses, we get 3x squared plus 6xh plus 3h squared. plus, distribute through the parentheses, 2x plus 2h. And then when we distribute the minus, we get minus 3x squared minus 2x all over h. And this is nice because some things are going to start to subtract out. We've got a 3x squared and a negative 3x squared. Those are gone. We've got a 2x and a negative 2x. Those are gone. So what we're left with is 6xh plus 3h squared plus 2h all over h. But we know we have to be careful when reducing. We must first factor before we reduce. So factor out an h, leaving behind 6x plus 3h plus 2 all over h. And now we can cross off those h's, giving us a final answer, a final average velocity of 6x plus 3h plus 2. That's how we calculate a difference quotient. There's several of these on the homework assignment. Make sure you take a really good look at them and understand how they work. The most common error we see is students forget to distribute the negative through parentheses. Always put that minus f of x in parentheses. And then simplify from there. So that kind of summarizes the first thing we want to do with a function, evaluating a function and a difference quotient. The next thing that I want to do is look at what is called the domain, or all possible inputs. And sometimes it's easier, instead of describing all things that are possible, we'll describe more what's not possible. And so far we've seen a couple things that are not possible. We know we can have no 0 in the denominator of a fraction. We also know there are no negatives in our even roots. Those both will make those functions undefined because we can't divide by 0, we can't take the square root of a negative number. Those make things undefined. So if we have a function like f of x equals 2x minus 3 over x plus 5, and we're asked is 5 in the domain, what we're really saying, can 5 equal x? Can we find f of 5? Well, here we have 2 times 5 minus 3 over 5 plus 5. Well, 2 times 5 is 10, and 10 minus 3 is 7, and 5 plus 5 is 10. Because we get an answer of 7/10, it doesn't matter what the answer is, but 7/10 is a valid answer, we say yes, 5 is in the domain. Let's look, is negative 5 in the domain? In other words, can negative 5 be an input or an x? Can we find f of negative 5? Well, that would be 2 times negative 5 minus 3 all over negative 5 plus 5. Simplifying, we have 2 times negative 5, which is negative 10, minus 3 is negative 13. But negative 5 plus 5 is 0. We can't do negative 13 divided by 0. We can't have 0 on the bottom of a fraction. I think about the word no. What's not allowed? No. 0 cannot be in the denominator of a fraction. No. Because that's undefined, it can't be in the domain. So we answer the question in the negative. Let's try another function. Let's take a look at the function f of x equals the square root of x plus 5. And we're going to look at the question, is negative 2 in the domain? Remember, we can't take the square root of negative numbers. But don't be too quick to exclude negative 2, because if we make that equal to x, if we find f of negative 2, that's the square root of negative 2 plus 5, or the square root of positive 3. Now, it might be an ugly number, but we can take the square root of negative 3. So we will say, yes, negative 2 is in the domain. How about this one? Is negative 7 in the domain? In other words, can we find f of negative 7 and get a valid output? Well, f is the square root of x plus 5, or negative 7 plus 5, which is the square root of negative 2. As we said earlier, we cannot take the square root of a negative number. So no, negative 7 is not in the domain. In fact, rather than looking at specific points, it might be easier to just find the exact domain of a function we're interested in. Let's do the function f of x equals the square root of x plus 1 over x squared plus x minus 6. Now with the domain, we need to look at what's possible and what's not possible. And remember, one thing that's not possible is the denominator. The x squared plus x minus 6 cannot equal 0. Well, if we tried to solve this, we would factor to get x plus 3, x minus 2 can't be 0. And then each factor equal to 0 or not equal to 0. X plus 3 can't be 0. X minus 2 can't be 0. So x cannot be negative 3 or positive 2. Those are outside of the domain. But in this problem, that's not the only restriction, because we have a square root. And we know with square roots, the x plus 1 has to be greater than or equal to 0, because it cannot be negative. Square roots cannot be negative. So x has to be greater than equal to negative 1. Well, if we really look at this problem, the negative 3 is already smaller than negative 1, so we don't really need to worry about that. So to clearly give our domain, we're going to say our domain is x has to be greater than equal to negative 1, and x cannot be equal to 2. That's going to be the domain of this function. One last thing I want to look at then is not just the domain, but looking at range values, or all possible outputs. Another way of thinking about that is all possible solutions. So if we had the function f of x equals 9 minus x squared, we could be interested in the question, is y equals 0 in the range? And when we're talking about range, that means we're going to plug the 0 in for the f of x. In other words, we're saying 0 is equal to 9 minus x squared. Well, we can solve this by adding x squared to both sides. Gives us x squared equals 9, and take the square root, x equals plus or minus 3. So we have two options, but what's important is, yes, we can get 0 for an answer. So yes, y equals 0 is in the range. Contrast that with the question. Is y equals 10 in the range? With range, we're plugging it in for the answer. 10 equals 9 minus x squared. And this time, if we subtract 9 from both sides, we get 1 equals negative x squared. Divide by the negative 1, and x squared equals negative 1. And then we try and take the square root. But we can't. We can't take the square root of a negative number. Because we can't do this, we will say no, 10 is not in the range of this function. Let's do one more range problem before we wrap up. Let's say another function, f of x is equal to x minus 1 over x plus 1. And we want to know, is y equal to negative 1 in the range? Again, we're going to plug that negative 1 in for the answer. Negative 1 equals x minus 1 over x plus 1. Solving, we're going to multiply both sides by the denominator of x plus 1, because it's going to divide out of the right, and we'll distribute on the left. Negative x minus 1 equals x minus 1. Adding x to both sides, getting all the variables on one side. Adding 1 to the other side gives us 0 equals 2x. Don't panic when you see 0. Just keep going. Divide by 2, and x equals 0. 0 is a valid solution. So we say yes, y equals negative 1 is in the range. What about is y equals positive 1 in the range? Well, we'll plug positive 1 in, so we've got positive 1 is equal to x minus 1 over x plus 1. Multiply both sides by the denominator again to clear it of x plus 1. Gives us x plus 1 equals x minus 1. Get the variables on one side by subtracting x from both. Notice x minus x is 0 and x minus x is 0. We're left with 1 equals negative 1. Except it doesn't. 1 and negative 1 are very different numbers, so we will say no, we never got an answer. Y equals 1 is not in the range. So domain, those are the inputs, the x values. Range, those are the outputs, the y values. The other thing we're doing today is evaluating functions at points and expressions, just replacing the variables with the stuff. Take a look at the homework assignment, practice especially with that difference quotient, and we will see you in class. In section 2.2, we're going to actually start working with functions a little bit with what's called the algebra of functions. And the first thing we're going to do is really quick because it's so simple. It's the basic operations that we can do to combine functions. This is your basic add, subtract, multiply, and divide. And so to set this up, I'm going to need a couple functions. So we're going to do f of x is equal to x squared plus x minus 6. And then we'll also use a g of x function, which is x squared minus 9. And the functions that we're going to look at are adding, subtracting, multiplying, and dividing. So if I were to add two functions, the way we notationally do this is we will say f plus g of x. And what that really means we want to do is we want to take f of x and add to it whatever g of x is. Now we might have a number and we could plug those in first and then add the results, or we might have just our functions like we do here and we'll just add these functions together. So f of x, that's this first one, the x squared plus x minus 6, and we'll always put it in parentheses when we make this substitution. And we add the g of x function. Well, g of x is this x squared minus 9. And then from here all we have to do is any simplifying that comes out of it. Since we're adding, the parentheses don't really matter, so we'll combine like terms. X squared plus x squared is 2x squared plus an x, and then minus 6 minus 9 is minus 15. And we have now added these two functions together. This idea works much the same way with subtraction. If we wanted to find out what f minus g of x was, what this really means we're going to do is we're going to take this f of x and we're going to subtract whatever g of x is. And again, if we had the numbers, we could plug those in for f and plug them into g and then subtract the answers. Or in this case, we've got the functions. So f of x gets replaced with, parentheses again, x squared plus x minus 6. And the g of x gets replaced minus, in parentheses again, with x squared minus 9. And this is important because in this case, the negative is going to distribute through the parentheses. When we do that, we have x squared plus x minus 6 minus x squared plus 9. Notice the sign change went all the way through the parentheses. So now when we combine like terms, x squared minus x squared is 0. We still have an x, and minus 6 plus 9 this time is a positive 5. No, it's not. Is a positive 3. And so we end up with this x plus 3 for our solution. So adding and subtracting, just adding and subtracting the parts. And as you might imagine, multiplying to be the next operation, we'll say fg of x is really saying we take the f of x function and we multiply by whatever the g of x function is. And again, if we had the numbers, we would plug them into f and plug them into g like we saw in the previous video, and then we would multiply those solutions together. But in this case, we just have functions. They're off my screen here, but they should be on your notes. F of x we know is x squared plus x minus 6. And the g of x that we're multiplying by is x squared minus 9. And because we put these in parentheses, we know that the operation is going to be a FOIL type thing where we multiply x squared times x squared is x to the 4th, x squared times negative 9, then x times x squared is x cubed, and x times negative 9 is negative 9x. And finally, 6 times x squared is negative 6x squared, and 6 times 9 is 54. And so to finish this out, we combine like terms. There's not a lot of them. We've got an x to the 4th, an x cubed, the like term, 9x squared minus 6x squared is going to be minus 15x squared, and finally a minus 9x, and a plus 54. To give us our final product. The last operation, as you might assume, is division. We show this by putting f over g of x. And again, what that really means is simply we're going to take the f of x function and we'll divide by the g of x function. Maybe do any reducing if we think it might be possible. So f of x, again, we said was x squared plus x minus 6. And then we divide, put it over the g of x function, which we know is x squared minus 9. Now, you remember from our previous unit when we were simplifying rational expressions, before we do any reducing, we have to factor the numerator and denominator. The numerator is x plus 3, x minus 2. The denominator is a difference of squares, is x plus 3 times x minus 3. And we see those x plus 3's can divide out. And so we have our final solution for the quotient, x minus 2 over x minus 3. Now these adding, subtracting, multiplying, dividing functions, really simple, really straightforward. We either do it with the functions, or if we have the numbers, we plug in the numbers and do it with the numbers. What's a little bit more involved and a little bit more appropriate for this level of coursework is going to be section B here, which we're going to call the composition of functions. And this is where we really start to take a look at functions inside of functions. The way we'll notationally show this is you will see an f with a g of x inside of the f. In other words, we're going to replace the x in f with g. In other words, that inside stuff is going to go into the f function. Maybe it'd be better to show it with a few examples. If we make f of x equal to x squared minus 2 and g of x equal to x plus 5, we could be asked to find f of g of x. And what I want to notice is this g of x inside, g of x is x plus 5. What we're essentially asking to do is take f and replace the guts with the x plus 5. Well, the guts in f, that's the x squared. So now that becomes, instead of x squared minus 2, it's stuff squared minus 2, and that stuff is the x plus 5. We can do a little simplifying with it. Squaring it, we get x squared plus 10x plus 25 minus 2, and that just gives us the like terms at the end. So for our final composition for f of g of x, we have x squared plus 10x plus 23. Kind of visually what we're doing here, this kind of feels weird, but if you remember that function machine that we started with, we have a function machine that's g of x and another function machine that's f of x. And basically we're plugging in x into the first equation and out comes g of x. And we plug that into the second equation, and out comes f of g of x. We're plugging something in, getting a result, and plugging it into the next function. Now I want to notice something here. If we switch the order and try and find g of f of x, now the f of x is the inside stuff. So this f of x, the x squared plus 2, is what's really on the inside. Now it's g of x squared plus 2. That is now the guts of the problem. which means that's going to go into G, where we see the x. It's now stuff plus 5. Stuff plus 5, and that stuff is x squared plus 2. Combine like terms, and we'll end up with x squared plus, oops, it's x squared minus 2, isn't it? Backing up. It should be a minus 2 each time. Don't change the sign. Keep the sign the same. So x squared plus 3 when we combine like terms. And I want to notice that f of g of x and g of f of x were two very different results. Sometimes they're the same, and that'll be more interesting to us later. But what's interesting here is right now, in general, they are very different results. So the order does matter. And we can do the same exact process with a number. We can find f of g of, let's do 3. And on the inside we see this g of 3. Essentially what it's asking us to do is go back to g and find 3 plugged into that. So g of x is x plus 5. So we're going to do g of 3 is 3 plus 5, or 8. That means f has inside it the result of g of 3. It has that 8. So all we need to do now is plug that 8 into the f function, into that x squared minus 2. So instead of x squared minus 2, it's stuff squared minus 2. We take that answer we just found. 8 squared is 64 minus 2, gives us 62 for a result. We could have also, instead of finding out what g of 3 was and plugging that answer into f, we could have gone up to that f of g formula that we found in step 1 and plugged our number 3 into there, and we would have gotten the same exact result of 62. Again, if we change the order, though, it does make a difference. Let's do g of f of 3, changing the order. Essentially, we first have to find f of 3. And remember, f was stuff squared minus 2. So if we plug a 3 in there, we get 9 minus 2, which is 7. So essentially, that inside stuff is 7. We're finding g of 7. And remember, g is just stuff plus 5. You should have that up on your notes a bit. What we're really saying is now 7 plus 5 is equal to 12. So g of f of 3 is 12. Again, very different from f of g of 3. The order is going to make a very big difference. So this composition of functions, this is going to be really the essential part of this video. So let's try a few more examples to help us see functions inside of functions. Let's look at f of x equals the square root of x plus 9, and g of x equals x squared plus 6x. First, we're going to find f of g of x. So again, g of x, the inside stuff, inside of the f function, is that x squared plus 6x. So we're going to take that stuff and stick it into the f function. Into the square root of stuff plus 9. And that stuff is x squared plus 6x. Notice we see the g inside the bigger function. Now, in terms of simplifying, you might notice what's under that square root can factor. That is x plus 3 squared. And we have the square root of a square, so this comes out to be x plus 3. Let's try and compose them the other way. Let's compose g of f of x. And this time the inside function is f. So inside g, we're going to see that f, the square root of x plus 9. So we're going to take that square root of x plus 9 and replace the x's with it in g. So stuff squared plus 6 times stuff, that stuff is square root of x plus 9. Square root of x plus 9. Only simplifying here is square and square root are inverses, so we're left with x plus 9 plus 6 square roots of x plus 9. And we have our simplified solution. Let's do another example. How about f of x equals x squared plus x, and g of x equals 1 over x plus 3. And we're going to find first f of g of x, then we'll go back and find g of f of x. So again, g of x, the inside stuff is this fraction, so we've got f of that fraction, 1 over x plus 3. So that fraction goes into replacing both x's. So f is stuff squared plus stuff. That's 1 over x plus 3 squared plus 1 over x plus 3. We could stop there. Let's do a little simplifying, though, just to practice our algebra with fractions. Squaring both top and bottom, we have 1 over x plus 3 squared plus 1 over x plus 3. To get a common denominator, we need another x plus 3 factor. Let's go with a different color. And that's going to give us 1 over x plus 3 squared plus x plus 3 over x plus 3 squared. Combining like terms, then in the numerator we have x plus 4 over our common denominator of x plus 3 squared. We have our composition. Now I'm going to have to scroll down to do the second example, the g of f of x, but you should have in your notes what g and f look like up above, so I don't have to keep scrolling. But again, we're going to have g of whatever that f of x function was. That f of x function was x squared plus x. So that's what's going into g. G was 1 over stuff plus 3, which is simply x squared plus x. It doesn't factor, there's not really any simplifying. That's going to be our final 1 over x squared plus x plus 3. That is our final composition. Now here's an interesting one. Let's say, oops, not C, this is number 3. Let's say f of x equals 3x minus 3x minus 5 over 4x minus 3. And we're going to find f of x. We're going to compose this fraction with itself. In other words, f of x, that's this whole thing here, is going to be inside the function. F of 3x minus 5 over 4x minus 3. So that means each of these x's is going to be replaced with this stuff. So we've got 3 times 3x minus 5 over 4x minus 3 minus 5 all over 4 times 3x minus 5 over 4x minus 3 minus 3. To help us out, I'm going to get rid of those compound fractions. And if you remember from our previous unit, we get rid of compound fractions by multiplying each term. Terms are separated by plus and minus. There's 2 on top, 2 on the bottom. By the common denominator, which is 4x minus 3. 4x minus 3. 4x minus 3. 4x minus 3. And when we do that, the first sets of 4x minus 3's divide out top and bottom. And so we're left with 3 times 3x minus 5 minus 5 times 4x minus 3 over 4 times 3x minus 5 minus 3 times 4x minus 3. Not difficult here, just a little bit of algebra, distributing through top and bottom. So we'll have 9x minus 15 minus 20x plus 15 all over 12x minus 20 minus 12x plus 9. Finally, combining like terms to finish it off, 9x minus 20x is negative 11x. 15 minus 15 is 0, that's nice, over 12x minus 12x is 0, and negative 20 plus 9 is negative 11. So in fact, we can reduce from there. The 11's divide out, and we're just left with x. Very interesting that this was just left with x. This means something important, which we're going to investigate more tomorrow. But for now, the algebra steps of just composing f with itself and simplifying is what we're going to be practicing on. In fact, we're not just going to compose things together, we're also going to decompose. The idea here is we're trying to identify an outer function, f of x, and an inner function, g of x. If we can identify the pieces of a problem, it's going to help us better identify the patterns we can use to solve the problem. So for example, if I have this function h of x is equal to the square root of 2x minus 3 over x plus 5, what I want to notice is we're taking the square root of stuff. That stuff on the inside we're going to call our inner function, g of x. Inside the square root is a function that could stand alone, the 2x minus 3 over x plus 5, that has been stuck inside this outer function. The outer function takes the square root of the stuff, and so we will just call that x. H of x is really a composition, f of g of x, where f is the square root and g is the inner function of that fraction. So for example, if h of x equals x plus 5 to the 2/3, plus 3 times x plus 5 to the 1/3 plus 2. What you might notice is, again, we've got an inner function. A couple ways you could call this inner function. One way is we could call the inner function the x plus 5. G of x equals the x plus 5 inner function. F of x is the function built around it, which is the stuff. Delete that. Let's just get an eraser. Which is the stuff raised to the 2/3 power. So we say x to the 2/3 power. Plus 3 times the stuff to the 1/3 power. Plus 2. But that's not necessarily the only way to think about it. What if we took the 1/3 part with it? G of x could have been thought about as x plus 5 to the 1/3 power. This is probably more useful if we're trying to identify quadratic in form, because then the outer function is the x plus 5 to the 1/3, all that stuff squared, plus 3 times that entire stuff, plus 2. Both of these are appropriate decompositions. The second one's probably more useful to us, because if we can see the pattern, the composition of the function inside a function, it turns into quadratic in form. That makes it more useful to us to work with. In fact, we can extend this idea out to several variables. Let's say p of x is equal to x squared plus 5 over x squared minus 2, and the whole thing is to the 3/4 power. Now what you might notice is in the very innards this repeated thing of x squared. We're going to call that our most inner function, h of x. Then around that is built a fraction function. Call that g of x. That fraction is the stuff plus 5 over the stuff minus 2. And notice when you stick h in there, it gives you the whole thing, with the x squared plus 5 and the x squared minus 2. But then all that is built in a bigger outer function, which takes all of that stuff, we'll use f for the outer function, takes all of that stuff and just raises it to the 3/4 power. And so p of x is a combination of these three functions. By identifying how we can decompose the functions, it's going to help us as we graph, as we solve, and continue to work with these functions. So we looked at the basic operations to start out with. We're not going to spend a lot of time on those because they're easy, they go fast. But composition and decomposition are really going to be the meat of today's lesson. Take a look at it on the homework and come to class with questions. In section 2.3, we're going to take a look at an important property of functions called inverse functions. And so first, to kind of define what we're talking about with these inverse functions, we're basically asking for a function that undoes something that has been done. This is your Control-Z function. And to kind of introduce this visually, what we're talking about is we've already talked about a function machine, f of x. And what we're suggesting in this video is for every function machine, there is another machine that's very closely related to it that we're going to call the inverse function machine. And the way we notate the inverse function is really similar to the regular function. We're just going to put a little -1 up above. That's not very clean. Let's try that again. a little -1 up above in between the f and the x. And that's not an exponent. I know it looks like an exponent. We do that just to make it confusing. When we see that f to the -1x, we read that as the inverse of f of x. This is the function that undoes what the f of x function does. In other words, if we were to take the number 5 and throw it into the regular function machine, it'll come out different, maybe a -2. The idea is if we take this -2 and plug it into the inverse function, it's going to spit out what we started with, a 5. Maybe a more general way is we're going to plug in an x to the function, we get a y out. The inverse takes the y as an input, and it spits the x out as an output. It takes you back to where you started. And you might notice this setup is really similar to how I visually depicted a composition of functions. In fact, the concepts are related because if we want to check if functions are inverses, the way we do that is we compose the functions. And when we do that, it should equal x. And the reason for that is what we just did here a second ago in this example. When we plugged x in, we got y, and then when we compose it, we get back to x. The composition will equal x if the functions are indeed inverses. So for example, if we had f of x equals the square root of x plus 5, and g of x, another function, the opposite of square root is to square something, the opposite of adding 5 is to subtract 5, so we might assume that the inverse function is x squared minus 5. The way we verify this is we find the composition f of g of x. Well, g of x, that inside stuff, is x squared minus 5. And so when we plug that in for the x in f, we get the square root of x squared minus 5 plus 5. And then we start simplifying. -5 plus 5 is 0, so we have the square root of x squared. And the square root of x squared is simply just x. We have, in fact, shown that these functions are inverses if we limit the domain, but we'll talk more about domain later in the video. Let's do one more example where we check to see if two functions are inverses. Let's say f of x equals 2x minus 3. G of x, then, we would assume we're going to do much the opposite. So instead of multiplying by 2, we'll probably divide by 2. And instead of subtracting 3, we'll probably add 3. So it would make sense to say that we have inverses. The last example, we showed that yes, they were inverses, because we did a composition, and the composition equals x. So let's see if the composition equals x here. We'll take f of g of x. Well, that means we stick g of x inside the f function, which is x over 2 plus 3. And if we plug that x over 2 plus 3 in for the x, we have 2 times x over 2 plus 3 minus 3. And then we can start simplifying. We'll distribute the 2 through, and when the 2 goes on the fraction x over 2, we're just left with x. And 2 times 3 is 6 minus 3. What you notice this time is we end up with, if I could change colors, whoops, too far, x plus 6 minus 3. When we combine like terms, we get x plus 3, not x. These are not inverses. For them to be inverses, their composition would need to equal x, and this one equals x plus 3, so that does not work. So if it doesn't work, how are we going to actually find the inverse? The way that we find an inverse goes back to this picture. Notice for the inverse function, instead of x going in, we have y going in. We've almost swapped the roles of x and y with the inverse function. Now y is the input and x is the output. So that's what we're going to do to find the inverse, is we're going to swap x and y. And y, remember, is what's really being represented with the f of x, the function notation. So if we've got an equation such as f of x equals x minus 3 to the 5th plus 2, we'll think about that f of x as a y, and then we will swap the x's and y's. So instead of y equals, it's now x equals. And instead of x minus 3, it's now y minus 3 to the 5th plus 2. Generally, equations are solved for y, so we're going to do that here as well. We're going to solve our function for y. And we do that by subtracting 2 from both sides. X minus 2 equals y minus 3 to the 5th. Get rid of the 5th power with the 5th root of both sides. 5th root of x minus 2 equals y minus 3. And finally get the y alone by adding 3 to both sides. And we get 3 plus the 5th root of x minus 2 equals y. Or since it's alone, we'll say now that is our f inverse function. So to find the inverse function, we simply swap our x and our y values. It works with equations of all types, but it also works with graphs. Let's take a look at this graph here. Let's put a point on the graph here at negative 2, 3. We'll do a point on the graph here at 1 or 0, 1. And we'll do a point on the graph here at 2, negative 1. And I'm going to connect them with a loop and a loop. Now if we wanted to graph the inverse of this function, the inverse is going to do much the opposite thing. The x's and y's are going to switch, which means this first point, negative 2, 3, is going to switch orders to now being 3, negative 2. So I'll put a new point at 3, negative 2, which represents that xy being switched. Similarly, the 0, 1 is going to flip to now be 1, 0. Similarly, the 2, negative 1 is going to flip to become negative 1, 2. And now when we connect the dots in much the same shape, but this time switching directions, we end up with this looking inverse, if my green dot doesn't disappear. Notice the shape is exactly the same where it leveled out flat. Now it leveled out going up. It's kind of flipped all those x's and y's around, giving us our new graph. Well, there's a little problem with this method, though, that we've kind of avoided up till this point. And that is if we want to make the inverse a function. First, a definition. A one-to-one function has one input for each output. And this is similar to our definition of a function. A function had one output for each input. This, a one-to-one function, is the opposite. One-to-one function is going to pass not the vertical line test, but the horizontal line test. The idea is the inverse is going to tilt it on its side and turn it backwards. When it's tilted on its side, is it going to still pass the vertical line test or the horizontal line test before it was flipped? So here's a problem that's not one-to-one. This is a problem. Let's consider a graph like x squared plus x minus 2. If we were to graph this guy, a rough sketch of what it would look like would be something like this. There's a point over here at -2, 0. There's a point over here at 1, 0. And there's a point down here at the bottom that's -1/2, -9/2. And if I were to try and graph the inverse function, -2, 0 would flip around to be 0, -2. And 1, 0 would flip around to be 0, 1. And -1/2, -9/2 would flip around to be -9/2, -1/2. Notice this is not a function because it does not pass the vertical line test, which goes through the function in more than one spot. And that's not allowed. That's because this blue function was not a one-to-one function, because if I were to draw a horizontal line, we've got the same problem. A horizontal line goes through it in more than one place. And so what we're going to do to fix this problem is we're going to eliminate the inconvenient part of the graph. What we're going to do for our solution is we are going to limit domain so it is one-to-one. In other words, if I look at my function, there's a left side and a right side to this blue graph. If we were to get rid of one side, and it doesn't matter which, let's say I cross off the left side, now you see that it is one-to-one, because that's going to turn into the bottom of the function, and if I get rid of the bottom of the function, just the top is there, and now it does pass the vertical line test. Now it is a function. So we limit the domain of the original problem. How about we do it with inequality symbols? That'll be good enough. We're going to say x has to be greater than or equal to that starting x value of -1/2. And if we restrict the domain, we've gotten rid of that extra arm that violated the vertical line test in the inverse or the horizontal line test of the original problem. We want to make the original problem such that a horizontal line is only going to cross at one point. Now that does provide choices, though. Sometimes there's more than one, oftentimes more than two, choices as to how we restrict the domain. For instance, look at this graph. Let's say this point over here on the left is -2, 0. This point at the first top is -1, 3. Point down here at the bottom is 1, -2, and we've also got 3, 0. And I guess you also noticed it went through the origin, so we'll call that one 2, 0, 0. Choices in how we restrict the domain. You notice if we were to draw a horizontal line, it's going to cross in 1, 2, 3 places. It's not going to pass the vertical line test when we make it into an inverse. So what we're going to do is we're going to restrict the domain so that it only crosses in one place. The catch is there's several options for this. One option is if we just look at the left part of the graph, the yellow. That would pass the vertical line test if we flipped it over. So doing that, we're limiting the domain to x is less than, because we want the left half. The x value there is -1. And so if we just look at x less than -1, we've got a point at -1, 3, which flips around to become 3, -1. Let's make it green. 3, -1. And the -2, 0 is on this line, which flips around to become 0, -2. And the graph becomes this guy. This lower part is the inverse of our function. But we didn't have to cut it there. We could have cut it and said, gee, we want the middle part of the graph, because that'll also pass the horizontal line test. If we do the middle graph, we're saying x is between our two x values of -1 and 1. Staying between those x values of -1 and 1, we end up with the edges at -1, 3, which when flipped becomes 3, -1, 0, 0, and 1, -2, which when flipped becomes -2, 1. And then if I connect these dots, we get this little guy, which is a function. Of course, we could have cut it and just kept the right side. If we do just the right side, we're saying x is bigger than that x value of 1, and we can graph that inverse. So the first part, the endpoint, it starts at 1, -2, which when flipped is -2, 1. Goes to 3, 0, which when flipped is 0, 3. And then it goes up forever from there. So this graph that we started with, which was really wavy, had 3 options for how we can slice it in order to determine the inverse. As long as the inverse is still a function passing the vertical line test, it still will pass for our final solution. So there's 3 answers for this problem. Other problems are maybe more than 3. Some of these are, there's no set one answer, as long as your answer passes the vertical line test. So let's combine this idea of one-to-one and restricting the domain with actually finding inverse functions. So this is going to be letter D. First we're going to look, is it one-to-one? And then we're going to find the inverse function. And if it's not one-to-one, to find the inverse, we may have to restrict the domain. So our first problem we're going to look at is f of x equals x plus 4 over x minus 3. And to help us out to determine if this is a one-to-one function, we're going to have our calculator do the graphing for us. In our next unit, we're going to look at how we can actually graph this without a calculator. But for now, we're going to use our calculator to help us. And if you hit the y equals button on your calculator, it'll take you to a place where you can type in your functions. Now with fractions, we're going to need to put parentheses around the numerator and denominator so the calculator knows the entire x plus 4 goes in the numerator, close the parentheses, divided by x minus 3, close the parentheses, and if we hit enter, we've now got that function listed in the y1 equals. The way we graph this function is we hit the graph button in the top right corner above the arrow keys. And the graph will slowly draw a picture for us. And what I want to notice is if we were to draw a horizontal line through this graph, it would only cross the graph at one place. Since this does in fact pass the horizontal line test, it is one-to-one, and we can go ahead and find its inverse the way it is. Now it's possible your graph has a vertical line through at the point 3, at x equals 3, a vertical line. If there is a straight up and down vertical line, what that actually is that's a that's a vertical asymptote. You can actually get rid of that vertical asymptote if you hit into the mode and scroll. There's a lot of options here in mode. Scroll down from connected and scroll over to dot, and that'll get rid of any asymptotes you might have. It'll make the graph a little more pixelated, but it gets rid of that asymptote. I like to keep connected on. Some calculators recognize it's an asymptote and some don't, so some may draw that vertical line in and some may not. But just know if you see a vertical line, that's probably an asymptote. That's not actually part of the graph. Okay, what's important though is we know it is a one-to-one function. We can just make it the f of x into a y and then switch the x's and y's around. So we've got x equals y plus 4 over y minus 3, and then begin solving for y. Clear the fraction by multiplying by the common denominator of y minus 3. We have y's on both sides, but we saw this in our previous unit. We know we need to multiply everything out and get the y's onto one side, everything else on another side. So I'm going to distribute the x. So we have xy minus 3x equals y plus 4. Let's move the y's to the left. We'll subtract y from both sides and move everything without a y, the 3x, to the other side by adding 3x. Be careful about like terms. We've got xy minus y equals 4 plus 3x. Those aren't like terms, so we can't combine them. But what we can do is factor a y out of the left side, leaving behind x minus 1 equals 4 plus 3x. Get the y alone by dividing out the x minus 1. And y is alone. We now know what f inverse of x is. It is going to be the 4 plus 3x over x minus 1. So it is one-to-one, yes. And we found the inverse function. No need to restrict the domain because it was one-to-one. Let's try one last example. Let's consider f of x equals x to the 4th minus 1. We're going to bring our calculator back, hit the y equals button. It should default to highlighting that first equation, and if you hit the clear button right underneath the arrow, it'll delete out that old function. And now we can type in x to the 4th power. We get an exponent by going right above the divide sign. 4th power. In some calculators it'll stick you in an exponent, in other calculators it'll actually draw the little caret symbol. If you are actually physically up in the exponent, you need to scroll over to get out of the exponent. Minus 1, and then we hit graph. And there is our function. Almost could sketch copy of it here. What our function did was it came down and bent and came back up. And the important thing here is to notice it does not pass that horizontal line test. We are going to have to restrict our domain. It doesn't matter which side we restrict, we just need to get rid of part of it, so I'm just going to get rid of the left side. Which means I'm basically interested in when x is greater than or equal to, what's our x value down there in the center? X is greater than or equal to 0. So that restricts the domain. Now we're ready to find our inverse. Remember, f of x is really y. So if we switch x and y, we get x equals y to the 4th minus 1. Add 1 to both sides, and x plus 1 equals y to the 4th. Get rid of 4th power with a 4th root. And because we are only interested in the right side, we're only interested in the positives, we don't have to worry about plus or minus. We just went to the right side. So y is equal to the 4th root of x plus 1, or we could say f inverse of x is the 4th root of x plus 1. We now have our inverse. So that's what we're looking at today, finding inverse functions by swapping x and y, whether that's in the function or that's on the graph. We're also looking to check if things are inverses, and the way we check them is we compose the two functions together. The only thing to be careful of as we begin finding these inverses is if we don't pass the horizontal line test, we have to restrict our domain, cut off part of the graph, so that when we find the inverse, it will still be a function. Take a look at the homework, practice, 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 and we will see you in class. Section 2.4 is going to take a look at some applications of functions, specifically around the quadratic equation. So just to kind of set this up visually, what we're talking about, I want to consider the graph of f of x equals ax squared plus bx plus c. And depending on what a, b, and c are, this graph is going to look like one of two things, maybe moved around, maybe a little wider, and maybe a little skinnier. It might look something like this, a parabola facing up, or it might look something like this, a parabola facing down. The way we tell the difference is if a is positive, if a is greater than 0, it points up like a smiley face, and if a is less than 0, it's going to point down like a frown face. What we're going to be specifically interested in today, though, is this point down at the bottom or at the top of the graph. Because what you should notice is that top of the graph is the maximum or highest point, and the bottom of the graph is the minimum lowest point. That point we call the vertex, which is either the min or the max, depending on the direction of the graph. And the way we can find this min or max is quite directly using the formula that the vertex of the x-coordinate is equal to the opposite of b over 2a. Notice it's the quadratic formula without the square root part. The opposite of b over 2a, that will tell us the vertex, or at least the x-coordinate of the vertex. And then the way we find the y-coordinate of the vertex is we simply plug that x point back into the function, and that's going to evaluate for us the y value. So this is kind of the big idea of today. You need to know how to do these two things and then be able to interpret them as well. So let's talk about the interpretation. The x-coordinate of the vertex tells us where or when the maximum or minimum value occurs. So if we want to know what value will maximize the volume of a box. We don't care about what the volume is. We just want to know when that maximum occurs. That's the x-coordinate. Versus the y value is what the maximum or minimum actually is. If we want to minimize our expenses, and I'm interested in what is that minimum expense, that's asking for the y-coordinate. So make sure you know what question we're asking. Are we asking when or where it's maximized, or are we asking what actually is the maximum value? So for example, we'll start with a really boring example that has no context at all. We're going to do f of x equals negative 3x squared plus 18x minus 7. If we want to know where the maximum of this graph is, we let the x vertex equal to the opposite of b, which would be negative 18, over 2a, and a would be negative 3. Again, we get our a, b, c, just like the quadratic formula, in front of x squared, x, and the constant, respectively. And so if we simplify this, we get negative 18 over negative 6, which is simply just 3. The vertex occurs when x is equal to 3. That's the where. The when. What is this maximum value? We plug that value that we just found of 3 into the function to find f of 3. So negative 3 times 3 squared plus 18 times 3 minus 7. And then it's just order of operations. 3 squared is 9, plus 18 times 3 minus 7. Multiplying gives us negative 27 plus 54 minus 7. And that is going to be 20, I believe. So the maximum occurs when x is 3, and that maximum value is 20. We'll never get an answer out of this function bigger than 20, and that happens when x is equal to 3. The assignment today takes a look at maximizing and minimizing lots of different application problems. Min-max problems. Now, I can't possibly go over all the different types of problems that you're going to see on the assignment without doing the entire assignment for you. Instead, I'm just going to do 4 examples that set up exactly what is going on with these min-max problems. Then your job on the assignment is going to be to take the context of the new problem, build your own equations, and go through the min-max process yourself. So first we'll start simple. We're going to find 2 numbers whose sum is 18 and whose product is a maximum. Looking at the information we have, we know we've got 2 numbers. So let's call those 2 numbers x and y. We know their sum is 18. X plus y must equal 18. And what we're asked to do is take their product and maximize their product. In other words, we want to multiply them together, x times y, and we want to maximize this. Well, we've got 2 equations, well, 2 parts. One's an expression, one's an equation. We want to maximize, so let's go back to that equation bit. And let's solve for one of our variables. Let's just solve for y. We can do that by subtracting off the x. Y is equal to 18 minus x. And what's nice there then is this 18 minus x, this constraint, can replace the y in our maximization. So we have x times 18 minus x. Well, if we distribute, that's 18x minus x squared. And actually, let's rearrange it, putting the x squared first. Negative x squared plus 18x. We now can find an a b, and a c, which is really 0, so that we can try and find this maximum. Notice this question is asking us to find two numbers whose product is a maximum. This is asking us to find when that maximum occurs. It's not asking us what is that maximum product. It just wants to know the pieces that make it a maximum. So here we're just looking for the x-coordinate of the vertex, which is the opposite of b, negative 18, over 2a, which is negative 1, or negative 18 over negative 2, which is positive 9. X is equal to a positive 9. So we found the first number now. The second number we can get by going back to that y equals equation. Y equals 18 minus x. And so we'll do that. The y equals 18 minus x, or plugging 9 in, 18 minus 9 equals 9. So the two numbers whose sum is 18 and whose product is a maximum are 9 and 9. Okay, that problem's really just a fun number game. Find two numbers who do this, maximize or minimize that. Let's do more of a application problem. Let's say a farmer is building a fence along a barn with two sections, as shown. So here's the barn. And the fence he's going to build is going to come out from the barn and go over, and then it's going to have a divider down the middle. So that's the fence. He has 100 feet of fencing. What size would give the maximum area? Well, we know area is length times width. And what's interesting here, as we maximize, that's what we want to maximize. Let's go ahead and write that maximization equation down. Area is length times width. That's what we're trying to maximize. But what I want to notice is that width is appearing 1, 2, 3 times. The length only appears once because we use the back of the barn for the other side. So we've got a length plus 3 widths to equal our total amount of fencing, 100 feet of fencing. Again, let's solve for one of the variables. Let's get the L alone, because that'd be the easiest. No fractions is 100 minus 3w. And so we can take that 100 minus 3w and replace the L in our maximization problem. We've got 100 minus 3w times w. And very similar to the number problem we just solved before, when we distribute and put things in a different order, we have negative 3w squared plus 100w. Again, this problem is asking for what size gives the maximum area. When does that maximum occur? We don't care what the maximum is. We don't care about the area. That's not what the question is asking. The question is asking what is the size of the fence. So that's just the x vertex formula, which is the opposite of b, negative 100 over 2a, which is negative 3. And we're just going to round this to the nearest whole foot. Negative 100 over negative 6. So 100 divided by 6, it's a positive 16.6. We can actually do that, 16 2/3 foot. So that's going to be the w that we have here in our formula. We should have said the w vertex. The w is 16 2/3 foot, 16 feet 8 inches long. We still need to find the length, then that's going to give us, in the length we've got this formula, 100 minus 3w. 100 minus 3w. And if we change that back into a mixed number, or an improper fraction to make the math easier, that's going to be 50/3, which is really nice because the 3's divide out, and 100 minus 50 is 50 feet. And we've got our dimensions. 16 2/3 for the width, 50 for the length, and we've maximized our area alongside of the barn. So you notice the process is pretty similar here, is we end up with a couple equations, something that we're trying to maximize. Oh, I don't like that highlighting color at all. Something that we're trying to maximize with two variables quite often, but we can simply take this constraint equation, solve and substitute in to reduce it down to one variable. And it doesn't matter how complex or difficult the problem becomes, the process is still the same. So for example, if we were asked to minimize, let's minimize something ugly. Let's make it s is equal to negative 3x squared plus 2xy plus 4y squared, given some constraint that we develop, such as 2x minus 5y equals negative 9. Okay, this is going to get ugly. There's going to be fractions. The process is the same, though. We've got this constraint. We need to solve for one of the variables. Let's just go ahead and solve for x. 2x equals negative 9 plus 5y. Divide both sides by 2, and x equals negative 9 halves plus 5 halves y. So now we take this chunk and plug it in for our x. This time we're solving for the x. Why did we solve for x? Because I'd rather divide by 2 than divide by 5. No real reason. Both methods would give you the same answer. So now what we're trying to minimize is 3 times x, which is negative 9 halves plus 5 halves y squared, plus 2x, which is negative 9 halves plus 5 halves y, times y, plus 4y squared. So let's evaluate exponents first. We've got negative 3 times 81/4 minus 90 halves, which comes out to 45. That's nice. No more fraction. Y plus 25/4 y squared plus 2 times negative 9 halves plus 5 halves y times y plus 4y squared. distributing through, the negative 3 and the 2 gives us negative 243 over 4 minus 135, plus 135y, don't lose that negative, minus 75 over 4y squared, minus 18 halves, plus, actually 18 halves, that's going to reduce to 9. Let's go ahead and just reduce that now. Minus 9 plus 10 halves reduces to 5y. Actually, I'm going to back up here. I want to notice we have to distribute the 2, but we also have to distribute the y through. So I'm going to treat that as 2y coming through. That way we've got the whole distributing. So it's going to give us negative 18y over 2, which again reduces to 9. If I can erase that 18. Negative 9y plus 5y squared plus 4y squared. Combine like terms. Before we do, let's get some common denominators here. On the y squareds, it looks like we want a denominator of 4. So I'm going to go ahead and do that. So the 5 I'm going to multiply by 4 over 4, and the 4 I'm going to multiply by 4 over 4. It's going to give us negative 243 over 4 plus 135y minus 75 over 4y squared minus 9y plus 20 over 4y squared plus 16 over 4y squared. Now when we add the y squareds together, we've got a common denominator, so we can add the exponents, negative 75 plus 20 plus 16. Let's get a different color here. Combining the y squareds will give us negative 39 over 4y squared plus the 135 minus 9 is 126y minus 243 over 4. Yes, there's fractions. Yes, it got ugly, but the process is still the same. What we've done is we took our equation and solved for a variable and plugged it into the original formula. A little bit of algebra makes it look like a quadratic, and so we can find the vertex. The x vertex, which actually is a y here, just to make it confusing, because y is our variable, is the opposite of b, negative 126 all over 2a, which is negative 39 over 4. I'm first going to simplify the denominator. 2 over 4 reduces to 2. And then, when we're dividing by a fraction, we're really multiplying by the reciprocal. So this is negative 126 times 2 over negative 39. And this is not going to reduce very well at all. A negative divided by a negative is a positive. I guess they're both divisible by 3. 126 divided by 3 is 42. 39 divided by 3 is 13. That's all we're going to get out of it. So 42 times 2 is 84 over 13. This is the y coordinate that starts to maximize. We can still get our x coordinate. Going back, remember x was negative 9 halves plus 5 halves y. X was negative, I've already forgotten, 9 halves plus 5 halves times the y, which was 84 over 13. we're going to need to get a common denominator of 26. So let's multiply by 13 also the other fraction. So that's going to give us 13 times 9, which is 117, plus 84 times 5, which is 420, over the common denominator of 26. 117 plus 420 is 537 over 26. So that's the x, and that's the y that will minimize this function. So the algebra got ugly, but the process was still the same simple process. I want to look at one more example before we wrap up here, though, going back to real applications. Let's say we've got 100 tickets sold. To a concert. If the cost is $3 per ticket. Of course, if we raise the price, we charge more, we make more money, right? Well, the catch is if we raise the price, we lose customers. For every 10-cent increase in price, it is estimated that one customer would be lost. What should be charged to maximize our revenue? One thing we need to know about revenue is generated, how much money comes in, is the price times the number sold. So we need to look at how these factors are going to work together. The price, the initial price for a ticket is $3. We're going to increase the price a 10-cent increment. So we're going to increase 0.1, I'll even say 0.10 just to emphasize the 10 cents. We're going to increase 10 cents, but we don't know the number of times. So I'm going to call that x. So if x is 5, that represents 5 10-cent increments. If x is -2, that means we're decreasing the price 2 10-cent increments, or decreasing it 20 cents. So x is the number of increments, number of 10-cent increments. The number of tickets sold then, we're starting with 100 tickets, but one customer is going to be lost for each increment. So we're going to subtract one customer, 1x, for each increment. This now gives us something that we can maximize. Multiply this out, gives us 300 minus 3x plus 10x minus 0.1x squared. Combining like terms and putting things in order, negative 0.1x squared plus 7x plus 300. And then the vertex on x is going to be at the opposite of b, negative 7, over 2a, 2 times negative 0.1, negative 7 over negative 0.2. Move the decimal over, we've got negative 70 over negative 2. which reduces down to 35. What I want to be careful here, though, is 35 is the number of increments that we determined were appropriate to maximize our revenue. The question is asking what should be charged. The question is really looking for the price, which means to get the price we need to look at our price factor, which is 3 plus 0.10x. We just calculated x, so 3 plus 0.10 times 35 increments, and that's going to be 3 plus 350, or $6.50. If we charge $6.50, we're going to maximize our revenue. We're going to bring in more money than the customers we've lost. But once we go above $6.50, we'll start to bring in less money than the customers we've lost. So $6.50 is really the ultimate best price to charge to maximize our revenue. Today's assignment, the problems can take lots of different forms. They're all going to fall on the same premise that we find that minimum or maximum on the quadratic ax squared plus bx plus c by finding the opposite of b over 2a. You're going to need to use the context, the problem, and stuff you know to build those equations. Sometimes you'll have to do a substitution, but the process and the pattern is always the same. Take a look at the homework. We'll see you in class tomorrow. Section 2.5 gets at some vocabulary that's going to be really important to us in this course, and especially for those of you that go on to a calculus course. We're going to use this vocabulary a lot. So today's lesson isn't so much mathy as much as it is learning the important vocabulary to read and describe the behavior of a graph. So first we'll start with the vocabulary, and then we'll do the examples, 2 examples, using the vocabulary after this. So vocabulary. First thing we need to know is the difference between domain and range of a graph. The domain is all the possible input values into a function. Generally, these are the x's. And the range is all the possible output values. Generally, we use the letter y to represent this. So, for example, if I've got a graph that starts here at -1, 2, and ends here at 1, -1, maybe it wiggles around like this, and I wanted to describe the domain. The domain is all the possible x values, and so what I could do is I could project this or squeeze this graph down onto the x-axis, or up, depending on the direction, onto the x-axis. And you see it covers everything from -1 to 1. That's my domain. If we were to squish it onto the x-axis, we would cover everything from -1 to 1. The range, similar idea, we're just going to go onto the y-axis. And if I stretch this guy onto the y-axis, whether it's from the left or the right, you'll see I go all the way up to 2 and all the way down to -1. So we say the range is -1 to 2. Domain is the x's, or the input values. Range is the outputs, or the y values. So that's the first vocabulary thing we need to know, domain and range. The second is we need to know the difference between when the graph is positive and when the graph is negative. Positive is when the output value, or the y value, is greater than 0. Not equal to. Should just be greater than 0. Or visually, when we are above the x-axis. Negative then is just the opposite, when the output or y value is less than 0. or when we are below the x-axis. So just a really quick example here. Let's say I have a graph that goes from here at -1, 2. It's going to come down, go through 0, 0, and back up. Actually, let's just make it go on forever. We would say the graph is positive wherever the graph is above the x-axis. So all the way to the left is -infinity down to 0. So -infinity down to 0. And then we will do a union. It goes back positive above the x-axis again at 2 all the way to infinity. Negative then is when the graph is below the x-axis, so this middle stuff. We always describe things by the x-axis. The x-coordinates are its location. So in terms of x, we're below the x-axis between the x values of 0 and 2. So we're negative from 0 to 2. That's the second. So first we had domain and range. Next we had positive and negative. The next one, don't confuse it with positive and negative, is when the graph is increasing or decreasing. And just like it sounds, increasing would be when the graph is going up from left to right. Decreasing, the graph looks like it's going down from left to right. So if I were to make a graph here, similar to graph to what we saw before. Let's have the graph go down. And bend up like this. Putting arrows on the end, decreasing, reading it left to right, we're going downhill, 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 downhill until it levels out. So the left part is all decreasing, and we always talk about x values, so we go from -infinity up to an x value of 0 here. So we're going to say that's decreasing, because the graph started going down, from -infinity to 0. Then you notice the graph goes up, 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 and keeps going up. We say then the graph is increasing on that range from 0 all the way up to an x value of infinity in this case. Notice it doesn't matter if we're above or below the axis. That would be positive and negative. Increasing and decreasing depends on if the graph is going downhill or uphill when we read it from left to right. The last thing we want to know, after domain and range, positive and negative, increasing and decreasing, the last thing we want to know are about asymptotes. First, we're going to talk about things called vertical asymptotes. And that is a line, a vertical line. The graph approaches but never crosses. Let me show you an example of this on a graph. We normally represent these asymptotes with We normally represent these asymptotes with dotted lines. So you might see a dotted line here vertically and a dotted line here vertically. Those aren't part of the graph, but instead those are lines the graph is going to grow close to but never actually touch. So this graph comes along and it's going to go up really sharp, but it's never going to actually touch. It's going to get closer and closer but never touch. And then on the other side you might see the graph start close, get away from it, and then go back towards being close again. It might go up, it might go down. And then here's another part of the graph. Notice those vertical lines the graph never touches. Gets close to, but never touches and never crosses it. And vertical asymptotes are always x equals. We've got a vertical asymptote here at x equals -2 and a vertical asymptote at x equals 1. The graph gets closer and closer, but never crosses. Be careful not to confuse that with what we call our limits at infinity, also known as horizontal asymptotes. And this describes what is happening at the edge, what the graph is approaching. So for example, let me draw another graph here. Let's do this graph. We're going to put a vertical asymptote in this graph right here at 2. But that's not what we're talking about. That was number 4. Also going to put a vertical asymptote here at 1. But then I'm going to put a dotted line that goes horizontal at 2. That horizontal line is going to be my asymptote, or the limit at infinity. So the graph might bend down that way, might bounce up and wiggle around like this, and then it's going to come maybe up this way. And what I notice is the limits at infinity, on the edge, the graph is approaching y equals 2. It's going to always get closer and closer but never get there. It is interesting to note that the graph did cross the horizontal asymptote in the middle. Horizontal asymptotes are only describing what happens at the extremes, at the edges, not in the middle. So sometimes in the middle it will cross a horizontal asymptote, but it will never cross a vertical asymptote. So this is the vocabulary I want you to be familiar with: domain and range, positive and negative, increasing and decreasing, and vertical and horizontal asymptotes. To practice with this vocabulary, we're going to do a couple examples where I'm just going to ask you details about the graph. So first we need a graph, and I'm going to do my best to draw it and describe it as I draw it. So we've got a y-axis that goes up to 1 and down to 5. We're going to go left to 3 and right to 5. Then I'm going to draw in a vertical asymptote at -2 and a horizontal asymptote at -3. I'm going to put a point at -3, 0. Put a point at -1, 0. A point at 0, -2. A point at 2, -4. And a point at 4, -1. And the way we're going to draw this graph is it's going to come in by the vertical or the horizontal asymptote, bend up and go towards the vertical asymptote, Getting my vertical and horizontal backwards. Then come back down the other side to go through these points. And after it hits the top point, it's going to come down to the horizontal asymptote. So this is example 1. We're going to call this the function p of x. So first thing I'm going to ask is, what is the domain? Notice the domain is going to be if we were to bring the x-axis up, squeeze everything down onto x. When we do that, what you might notice is the only thing missing, the only thing that's not part of the graph is when we, when we delete the graph. That'll do it. Can't get rid of that little yellow piece. There it goes. The only thing missing will be that vertical asymptote at -2, because the graph never equals -2. So we'll say from -infinity to -2, then we have a union. We have to jump over the gap at -2, and then we will go from -2 to infinity. The range. Range is the y value. If we were to squeeze this graph onto the y-axis, what we see is the y-axis is covered even down here. What y values are covered in there? Well, what I see is it's going down to a lower point. The y ends here at, I think I lost an x line. What is that? -1, 2, 3, 4? -4 seems to be the bottom of the graph. But at the top of the graph, near the asymptote, it does seem to go up forever. So we will say the bottom of the graph is -4 on the y, but then it goes up forever to infinity around that asymptote. See, where is this graph positive? It's positive where it's above the x-axis. Notice it turns positive here at -3 and stays positive up until the asymptote. Now this is a special thing to note. At the asymptote, the graph is nothing, so it's not positive or negative. So that happens at -2, and then we're still positive coming down until we hit the point 1. So from -3 to -2, union, we have to jump over the asymptote from -2 to -1. So as you might imagine, negative would be everywhere else. It's down below the x-axis and negative on the left. It's negative on the right and never quite crosses the axis again. So from -infinity to -3, union, we drop negative again after 1, and then off to positive infinity. Increasing. Increasing. Where's the graph going up from left to right? Well, I do notice it is increasing initially, right up to the asymptote. So from -infinity up to the asymptote at -2, it's increasing. And actually, it's got a second time that it increases here in the middle of the graph, and that is from 2 to 4. So we'll say union from 2 to 4, it is also increasing there. So if I ask you when it's decreasing, decreasing must be the rest of it. From that asymptote, it's clearly going down, 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 So from -2 to 2, we always say the x-coordinate, describing its location. Union, it starts going down again from 4 on forever. So 4 on to infinity. We could even ask to describe the graph in terms of maximum and minimum points. If we say x is greater than or equal to 2, what is the maximum value that we hit? This is actually asking what is the maximum. That's asking for the y-coordinate. We want to know what the maximum actually is. So right of 2, you see we go up and we peak here. We peak at that value of -1. So we're going to say the maximum is -1 if we're greater than 2. And similarly, we could restrict it and say if we let x be greater than 1, what's the minimum? In other words, where is the valley that we hit? The valley that we hit greater than 1 is down here at -1, 2, 3, 4. So the minimum value for the graph in that range is -4. How about this? What's p of 0? P of 0, 0 is talking about the x-coordinate there, the input. We're looking for the output. So when x is 0, y is -2. This is a very different question than asking when p of x equals 0, x is equal to. Because now we're being told the output. We're being told the solution is 0. What are the x values that give you an output of 0? Well, there's one here at -1 and one here at -3. So x is -1 and -3. How about this? Let's see if I can scroll without losing too much of the graph so that we can still solve problems. K, when p of x equals 3, what does x equal? Actually, we'll make it -3. When p of x is -3. What I want to notice about -3, as I'm marking up this graph significantly, -3 is the asymptote. But because it's a horizontal asymptote, we are allowed to actually hit the asymptote. So we hit it once at 1 and once at 3. So x is equal to +1 and +3. I have two more I'm going to try and squeeze on here. When we write x arrow -2, what that means is we want to know what the graph is doing as it gets close to -2. Not actually on -2, but when it gets close to it. What's the behavior doing? What's it trending towards? When x is getting close to -2, p of x is getting close to what? Well, if we notice close to -2, that's the asymptote. The graph is going up, 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 up. It's going up to essentially infinity. And that's indeed what we're going to say here. P of x is going to positive infinity. Sometimes it'll go to positive infinity at an asymptote. Sometimes it'll go to negative infinity at an asymptote. Sometimes it goes both directions, and so we'll have to specify on the right side or the left side. And we'll look at that in our next example. I'm going to put m over to the left here. Should go under L, but I want to have enough room. Also interested, as x goes to infinity, where does p of x go to? In other words, as we go off the right side with a positive infinity of x, what's the graph getting close to? Well, the graph is getting close to that horizontal asymptote. That horizontal asymptote is at -3. So we bloodied all over this example with tons of color. But what I want to notice we saw and were able to evaluate is we found domain and range. We found where the graph was positive and negative. We found where the graph was increasing and decreasing. We found minimums. We found maximums. We found points on the graph, both solutions and inputs. We also looked at the asymptotes, and as the graph got close to the asymptote, what was the behavior doing near the asymptote? Because we'll never actually be equal to an asymptote, but what was it doing near? Let's do one more example, and then your assignment's full of examples. But one more example where we really work with this vocabulary. So we're going to go 4 to the left. We're going to go 3 up. Actually, let's go 5 up. And we'll go 5 down. And we'll go 6 to the right. Maybe 7. I'm going to put a point at -1, 0. A point at 0, -1. A point at 2, 0. And a point at 4, -2. Then what I'm going to do is I'm going to add some asymptotes. We're going to put a vertical asymptote at 3. We're going to put a horizontal asymptote at 3. And a horizontal asymptote at -3. All right. Now let's see about going through and filling in the graph. I want the graph to start close to that top horizontal asymptote. And it's going to come in, bend down, and it's going to go up as it gets close to that vertical asymptote. Then we're going to come in from the bottom, close to the vertical asymptote, hit our point, and then level out next to the asymptote. And we're going to try and find all the similar information about the graph. First, we're going to start with finding the domain again. Again, domain is all possible x values. And what you should start to notice is the graph hits all these x values until it gets to the asymptote. Then after the asymptote, the graph seems to hit all of the x values. The only thing this graph seems to miss are the asymptotes, that vertical asymptotes. So x goes from -infinity up to 3, where that asymptote is, and then union starting again from 3 up to infinity, basically jumping over the point 3. Range then? Range is the y values, and so if we look at how the graph touches the y values, notice we do go through the asymptote, coming down here, then again down here, and it goes all the way down. What I want to notice is there's actually a gap in the range between the lowest point on the left and the highest point on the right. We need to reflect that when we describe the range. So the range starting from the bottom goes from negative infinity up to that high point on the right at negative 2. And then union, we have to jump that gap. The range, the y values start again at negative 1 and go up to infinity. Next, I want to know, where is the graph positive? Remember, positive means above the x-axis. And we describe it in terms of what x values are above the x-axis. Well, notice this graph starts out above the x-axis, then it's below for a while, and then it's above for a really brief moment in time. So to describe where the graph is positive, it's positive from negative infinity off the left till negative 1. Union, it pops positive again from 2 to 3, and then it's not positive anymore. Negative, then, is when the graph is below the x-axis. And we describe it again in terms of the x's. So we've got this little lump that's below the x-axis, and then the entire right part is also below the x-axis. And so we're going to describe those ranges in terms of the x value. So we drop below the x-axis at negative 1, and we stay below all the way up till 2. And then union, after that asymptote from 3 to infinity, we are always negative. We're also interested in when the graph is increasing. Remember, increasing means going up left to right. Where does the graph begin going up? Right from 0. You see, from 0 we start going in an upwards direction all the way up, and then again after the asymptote, moving upwards again until we reach that maximum. Remember, with asymptotes, it's neither increasing or decreasing. It's undefined, so we can't count the asymptotes. We have to do the left part from 0 to 3. Union, jumping over the asymptote, from 3 till 4, describing the x-coordinates again. The graph is increasing, going up. Decreasing, then, when the graph's going the other way from the beginning. You notice it's going down, 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 and then from that maximum point, down, down, down. So from negative infinity to 0, when it turns the corner. Union, again from that 4 on to infinity, the graph is always going down. Not very fast as it gets close to that asymptote, but it's definitely always going down. You know what, I never named this function. Our previous function was Q, or was P, right? P of x. So we'll call this function Q of x. It's the next letter in the alphabet. That sounds nice. So we're going to find Q of 0 this time. Q of 0 is getting at finding when our input value, our x value, is 0. Notice x is 0 right here in the center of the graph. That's equal to negative 1. Again, that's different than asking when Q of x equals 0, the solution is 0, what does x equal? So now the solution, the y, the output is 0. That's these points over here on the left and the right. Our y values are negative 1 and 2. I'm sorry, the x values are negative 1 and 2. When x is negative 1 and 2, the solution is 0, the output. The y is 0. We could find a local minimum. The minimum when x is less than 2. When we go less than 2, that's the left half of the graph. The minimum is this point over here, where the valley is. Again, we're asking for the minimum, not the location. We already know the location. The minimum value is equal to that y value of negative 1. We can also ask for a local maximum when x is greater than 3. That's on the right side of the asymptote, and that's where the mountain peaks, the maximum there. The y value at that point, you see, is negative 2. Again, min and max, they're asking for what that value is, not where it is. Okay, let's look at this. As x gets close to 3, what does q of x approach or get close to? Notice on the one hand, on the left, it's going off to positive infinity. It's going up. On the right side of 3, it's down here at negative infinity. And so the way we're going to compensate for this difference is we're going to split this up, and we say when x goes to 3 from the positive side, over here to the right is the positives, over to the left is the negatives. As x goes to 3 from the positive side, q of x, the function, from the positive side is going down to negative infinity. Versus if x goes to 3 from the negative side, from the negatives it's going up to positive infinity. Q of x is approaching positive infinity. I'm going to put L off to the left just because I'm running out of space. L wants to know as x goes to plus or minus infinity, what does q of x approach? I'm going to clean up some of this mess. It's getting crowded. All this extra colors going on and arrows. So if you want to review anything, check out the rewind button. There, now we can start to see the graph again. Okay, as x goes to positive and negative infinity, again I want to notice at positive infinity, the graph is down here. The graph is at negative 3. At negative infinity, over on the left, we're up here at positive 3. So again, we're going two different places. So we're going to need to express the two different answers. As x goes to positive infinity, q of x is going to go to negative 3. But as x goes to negative infinity, q of x is going to go to positive 3. We're describing the end behavior, the edges of the graph. So that's really today's lesson. Not really very mathy. It's very much a vocabulary lesson. But it's vocabulary that's going to be very important as we work with graphs throughout this course. And very, very important when you get to calculus. Because when a certain graph is increasing or decreasing, it means something about its positive or negativeness. It has to do with this thing called a derivative. You need to know this vocabulary, know how to describe it, and know what it means as we work with these graphs. Lots of new vocabulary. It's very clunky when you start working with it. Practice, 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 practice is the way you get this vocabulary and really understand what it's talking about. So take a look at the homework, come to class with questions, and we will see you then. Section 2.6 gets at this idea of transformation of graphs. It's something we're going to plant on for 2 videos, actually. Today we're going to do it generally, and tomorrow we're going to make it more concrete with specific functions. We're going to look at how we can change the graph of a function, how we can move the graph of a function around. And as we do, there's 2 parts that we change. We change either the x or the y, or usually both. Now, changing the y is easiest, so we're going to look at that first. We're going to look at how the y changes with just the simple function that we're going to consider. The function f of x equals x. And if we graph f of x equals x, we should know it has a y-intercept of 0, a slope of 1. And so if we put 3 key points on here, the first one's going to be at 1, 1, 0, 0 is the second one, and the third one would be at -1, -1. And we're going to look at what happens when we take the function f of x and we add a number to it. Maybe we'll add 2 to the function. Well, the function used to be just x, and we said we were going to add 2 to it, so now it's x plus 2. And we're going to look at how this changes the y coordinate. Now, we should know that x plus 2 has a y-intercept at 2 and a slope of 1, so it's going to go something like this. And so we're looking at how y changes. We're going to keep the same x's we had before. So when x is 1, 1 plus 2 is 3. So we have 1, 3. When x is 0, 0 plus 2 is 2. So we have 0, 2 on the graph. And when x is -1, plugging -1 into the function, -1 plus 2 is a positive 1. And I want to notice how these x's, the x's we kept the same. The x's we kept the same at -1, 0, and 1. But we now have new y values. The y value of 1 has increased to 3. The y value of 0 has increased to 2. The y value of -1 has increased to positive 1. What does this mean for us? How are all these y values changing? What you should notice is what we've done is we have always added 2 to the y. Keeping the x the same, what we have done is we have added 2 to the y. So I want to notice adding a number to the end of a function adds that number to the y coordinate, which we might expect. I'm going to do a little similar exercise, but this time we're going to multiply our function by 2. We're going to take 2 times f of x. Now remember, f of x was just x, the simple function. So now we're going to multiply x by 2, and we now have 2x. And let's look at how that changes our graph. Well, we should know that 2x has a y-intercept of 0 and a slope of 2, so we know the graph is going to look like this. And if we plug in our known values of -1, 0, and 1, we're going to have new y values. When we plug 1 in, 1 times 2 is 2. We have 1, 2 on the graph. When we plug 0 in, 0 times 2 is 0. And when we plug -1 in, -1 times 2 is -2. And so I want to notice that while we kept the same x values again, -1, 0, and 1, the y values have changed. The y value that used to be -1 is now -2. The y value that used to be +1 is now +2. And the y value that originally was 0, whoops, wrong 0, the y value of 0, is still 0. And as you might guess, we're multiplying here because we multiplied the function by 2. You can tell we also multiplied our y values by 2. So that's what happens here. If the function gets multiplied 2, we multiply the y by 2 as well. And we're going to see this pattern no matter what type of function it is. If we multiply the function by 2, we multiply all the y coordinates by 2 as well. So that's kind of how we could change the y coordinate, kind of like we'd expect. Multiplying by 2 multiplies by 2. Add 2 increases by 2. Just what we expect with the y values. We're going to do a really similar exercise with the x values and look in part B how we can change the x values. And again, we're going to consider the same function, f of x equals x. And again, we should know that's a y-intercept of 0, 0, 0. And then we've got the point 1, 1, and -1, -1. And again, we're going to do the same thing. We're going to manipulate the function, but we're going to manipulate the part of the function that has the x in it. So we're going to keep the y values the same this time. This time we're going to keep y values of -1, 0, and 1. And we're going to look at how the x values change. So first we're going to find f of x plus 2. Notice we've added 2 inside the parentheses. Now the function really looks much the same. The x has been replaced with x plus 2, but that's the whole function. And so it's going to seem quite boring at first until we really look at what's happening. We know we've got a y-intercept of 2 and a slope of 1. However, this time we're going to keep the y values the same. So when the y is 1, we might even have to do a little bit of algebra. We're saying 1 equals x plus 2. Subtract 2 from both sides, and we find out that x is -1, 1. When the y value is 0, you can tell by looking at the graph, or by putting 0 equals x plus 2 and solving, we get when x is -2, y is 0. And you might notice the pattern will come up here and say instead of 0 equals, the other y value we want is when -1 equals the function, keeping the y value the same. Subtracting 2 from both sides, we find out that x is -3, -1. So again, we've kept the same y values in this problem because we want to see how x changes. Notice our x's went from 1 to -1, from 0 to -2, from -1 to -3. When we add 2 to the x coordinate, it seems our graph actually has subtracted 2 from each x coordinate. Notice this is different than the y's, which did exactly the same thing. Here the graphs are going to do the opposite, and we subtracted 2 from the x coordinates. So it kind of feels backwards with the x. We see plus 2, so we subtract 2 from our x coordinates. Similarly, if we multiply the x coordinate by 2, replacing the x with 2x, we get 2x. And that looks much the same as what we did last time, but again, this time we're going to be really interested in looking at what happens to the x coordinates when we keep the y coordinates the same. Well, our y coordinate of 0, 0 is probably the easiest to keep track of. It's still at 0, 0. A y coordinate of 1, though, if we make 1 equal to 2x and divide both sides by 2, we see the x coordinate is 1/2 when the y coordinate is 1. Similarly, if we do a y coordinate of -1 and divide both sides by 2, we find out that x is -1/2 when y is -1. So notice from the original graph, again, we've kept the same y values and looked at how the x values changed. The x values went from 1 to 1/2, and from -1 to -1/2. and from 0 to 0. Notice this time, instead of multiplying the coordinate by 2, this time what we've done is we have gone through and we have divided the x by 2. And this kind of feels weird and different. With the y values, exactly what we expected to happen. When we add a number, we add to the y coordinate. When we multiply a number, we multiply the y coordinate, just like we expect. The x's are much the opposite, because the x's are affecting the input. What they do is they move the point of reference. They move the input. What's happened is the background actually moves what we expect. And so if you could visualize example 1 here, the background, the grid has moved right 2. The graph stayed in the same place. And so when the grid moves right 2, it gives the illusion the graph or the line has moved left 2. And that's kind of what's happening with the x values. You see the opposite of what you expect to happen. And so to help us see that opposite, we come up with our translating rule here. Really generally, if y equals some number times the function plus a number, and then inside the function we multiply and add. So y equals a times f of cx plus d, adding b to the whole thing. The stuff outside of the function affects the y coordinate. To get our new y coordinate, we're going to call that y prime, our new y, what we do is we say we take a times y, notice the y replaces the f of x, plus b. It does exactly what we expect it to do. This is going to be an essential element for today and tomorrow's lesson. Y prime, the new y, we take a times the old y plus b. The x stuff all comes from inside the function. How the inside is being manipulated. And the inside is backwards. So it's not actually going to give us the new x, it's going to give us the old x equals the cx plus d. But this time the prime is on the inside. And so we're going to have to solve for the prime. So if we subtract d and divide by c, we find out what x prime is actually equal to. And that gives us that opposite relationship, because we had to solve the x's. Okay, that's about 15 minutes of theory. What's it look like when we're actually trying to make a graph? Let's look at a real graph. Let's say this is the graph of the function f of x. And on this graph, we're going to put on the point -3, 1. We're going to put -1, 3. We're going to put 2, -1. And we're going to put 3, 1. And the way we're going to connect this graph is kind of with a quarter circle looking thing. Then we're going to do a straight line, and then we're going to do kind of an upside down quarter circle. That is the function of f of x. We're going to attempt to graph the function y equals 1/2 f of 2x plus 3 minus 1. The outside stuff around the f of x is going to affect the y coordinate. So our new y coordinate, y prime, is 1/2 of the old y coordinates, that's all that f of stuff, minus 1. The inside stuff is going to affect the x coordinate. And remember, this one we're going to have to solve. X equals 2x prime plus 3. So when we solve, we subtract 3 from both sides and divide by 2 to get the new x prime, the new x coordinate. So looking at our graph, we were given 4 points. The first point was negative 3, 1. The second point was negative 1, 3. The next point given to us was 2, negative 1. And the next point given to us was 3, 1. Each of these points is going to translate and move to a new location, a new x, comma, y. That is what we are going to find. So first, let's look at the x's. Our formula to find our new x's is we're going to subtract 3 and divide that number by 2. So x's, that first column, negative 3 minus 3 is negative 6. Plugging into the x here in this formula in green at the bottom, x minus 3 over 2. So negative 3 minus 3 is negative 6, divided by 2 is negative 3. When I plug negative 1 in, the second point, negative 1 minus 3 is negative 4. Divided by 2 is negative 2. The third point has an x-coordinate of 2. So I plug that in for our x. 2 minus 2 is negative 1 half. And then finally, my last point is 3. 3 is my x-coordinate. 3 minus 3 is 0 over 2 is 0. What we've done is we found all of our new x-coordinates by plugging them into the x formula that we found. Now we'll do the same thing with the y formulas. Y prime is equal to half of the y minus 1. This might be easier if I have a common denominator. The common denominator here is 2, so if I make that minus 1, 2 over 2, we're going to have y minus 2 over 2. And that way I can just flow through. I could have done this common denominators every time or however, but we're going to work these new y's the same way. So we're going to plug these y's into y minus 2, and then we'll put it over 2. So 1 is my first y coordinate. 1 minus 2 is negative 1 over 2. 3 is my second y coordinate, so 3 minus 2 is positive 1 over 2. Negative 1 is my next y coordinate. Negative 1 minus 2 is negative 3 over 2. And then plugging 1 in for the y, 1 minus 2 is negative 1 over 2. We now have the new points for our graph. We're going to have to do a lot of scrolling here as I do this. The x's, I notice, go from 0 to negative 3. And the y's go basically up to 3 halves. There's -1, -2, -3, -4. And there's 1, 2, 1, 2. That's, you can split that into halves. Our first point was -3, -1/2. So we'll go -3, -1/2, and there's my first new point. The second new point is -2, 1/2. -2, +1/2. Here's my next new point. -1/2, -3/2. -1/2, -3/2. And finally, 0, -1/2. These are our 4 new points that we got off of our original 4 points. Now we're going to try and match the shape. We're going to have to curve up, straight line, and curve up. So we're going to match that here. We're going to curve up, straight line, and curve up. We match the shape. And this is now our new function. Our y equals 1/2 f of 2x plus 3 minus 1. This is a process that feels really clunky the first time you do it, but yet the steps are actually really similar. Notice what we did is we identified the parts that affected the y to come up with our y equation. We also identified the parts that affected the x to come up with our x equation. The x equation we had to solve for x prime. The y equation, it's helpful if you have fractions to write it as a single fraction, get a common denominator. And then using those formulas, we took all of our old x's to come up with new x's. All of our old y's to come up with new y's using those formulas. Then it's just connect the dots to get our new graph. So let's try one more before I let you go on the homework assignment. Let's do a real simple graph here. We're going to do 5 points here. -2, 1. -1, 0. 0, 2. 1, 0. And 2, 1. The way we're going to connect the dots is we're going to come straight down on the left, make kind of an upside down parabola looking thing, and then straight up on the right. So it's going to be kind of a symmetrical, I don't know what that's a picture of. That's what it is. We're going to call this the function g of x. I guess I should number this, huh? Let's call this number 2. We are going to find the graph of y equals 3, g of 1/4 x minus 2 plus 1. Again, what parts are going to affect the y-coordinate? The y-coordinate is the stuff around the function, and the function itself is the y. So our new y, our y prime, is 3 times y plus 1. That's going to be a really nice, easy formula for us to use. Times 3 plus 1, times 3 plus 1. Our x's are inside the parentheses, but remember we're going to have to solve, so it's backwards. X equals 1/4 x prime minus 2. So to solve, we're going to have to add 2 to both sides, and then we clear the 1/4 by multiplying by 4. And you can distribute if you want. I'm just going to do the order of operations, add 2, multiply by 4, add 2, multiply by 4. And that'll give us our new x coordinates. So, our points that we're working with are -2, 1, -1, 0, 0, 2, 1, 0, and 2, 1. We're going to apply these formulas we just found to find our new x coordinates and our new y coordinates. Then we'll be able to graph our new graph. So first the x's. We said order of operations, we have to add 2 and then multiply by 4. So -2 plus 2 is 0, times 4 is 0. That's our new x. -1 on the second point, plus 2 is 1, times 4 is 4. 0 plus 2 is 2, times 4 is 8. 1 plus 2 is 3. 3 times 4 is 12. And 2 plus 2 is 4, times 4 is 16. Those are our new x values. The y values, to get our new y values, we plug them in for y in the y prime equation. This y prime equation tells us we're going to multiply by 3 and then add 1. So in the first point, y is 1. 1 times 3 is 3, plus 1 is 4. Try 0. 0 times 3 is 0, plus 1 is 1. Plug in 2. 2 times 3 is 6, plus 1 is 7. Try 0. 0 times 3 is 0, plus 1 is 1. Plugging in 1. 1 times 3 is 3, plus 1 is 4. And so now we have our new coordinates. Notice the x's are going to have to get really big. Everything's in the positive range. So x is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We're going way out there. The y's are going to have to go up as high as 7. So we start plotting our points, 0, 4, 4, 1, 8, 7, 1, 2, 3, 4, 5, 6, 7, somewhere around there. 12, 1, and 16, 4. Then we connect the dots, keeping the same shape as the original function, the straight diagonal, the upside down looking parabola, and the straight diagonal. This now is the graph of y equals 3 times f of 1/4 x minus 2 plus 1. This is the process we're going to go through on these graphs. Every single problem is the same way. You look at the points that we know, and how are the y's going to change? That's what's happening on the outside around the function. How are the x's going to change? That's what's happening inside within the function, and we have to solve for that variable, giving all those opposite operations. Then just go through all our points. Change the x's using the x formula. Change the y's using the y formula. Take a look at these on your homework. You want to get really good at how these graphs move around before we start introducing the basic functions and how we can move those graphs around. If you can master today's lesson, tomorrow will be easy, easy, easy. So take the time to do well, look at the homework assignment, and we will see you in class. Now that we know how basic transformations work with graphs, we're going to look at some basic functions and how those functions can be translated. So, First, we need to know the functions. There are 6 functions that you need to know their shape, their location, their behavior in this class. The first function is what is called the linear function. And it is f of x equals x. The linear function is a straight line with a slope of 1 through the origin. The 3 key points that you should know are on this graph are 1, 1, 0, 0, and -1, -1. That is the linear function. The second graph that you need to know is the absolute value. The absolute value function looks like a V, as in the word value, with a slope of -1 down to the origin and a slope of +1 coming out of the origin. Essentially, we took the linear function and took that negative part and reflected it positively. Again, the 3 points you need to know in the absolute value function are 1, 1, 0, 0, and -1, 1. If you know those 3 points, you can graph an absolute value function. The third function we're going to look at is what is called the quadratic. Oops, I forgot to tell you what the absolute value function was. F of x equals the absolute value of x. Sorry about that. So the quadratic function is f of x equals x squared. And you've seen this function before. This function is your basic parabola function, the U shape, and it's got 3 key points, 1, 1, 0, 0, and -1, 1. Notice those are the same key points as the absolute value function, but the shape is very different. The absolute value is a very wide V, and the quadratic is more of a narrow U. The shape is important. The fourth function you need to know is a cubic function. The cubic function is f of x equals x cubed. And if you were to graph the cubic function, it's going to come up, level off, and go back up again. There's a little bit more of a leveling off on the left side. There. It's got key points that you need to know of 1, 1, 0, 0, and -1, -1. Again, you'll notice these are the same key points as the linear function. Ooh, the word cubic didn't get on there. Cubic. There we go. Same 3 key points of the linear function, but the shape is very different. The cubic is wavy, the linear is straight. 2 more functions. Function number 5 is called the inverse function. It's also called the reciprocal function. Reciprocal. Should have stuck with inverse. I know how to spell that. The reciprocal function is f of x equals 1 over x. And the way the reciprocal function works is it has 2 asymptotes. One is the x-axis, and one is the y-axis. And the reciprocal function is in the bottom left, bending towards those asymptotes, and the top right, bending towards those asymptotes. The key points you should know on here are that main bend point are at 1, 1, and at -1, -1. and that the asymptotes meet at the center point of 0, 0. Similar to the reciprocal function is function number 6, called the inverse square function. That is f of x equals 1 over x squared. This one also has the same two asymptotes, the y-axis and the x-axis. But this time the bends are going to be in the top left and the top right. Key points then are 1, 1, negative 1, 1, and then where the asymptotes intersect at 0, 0. So 6 functions. This is one of the few and only, I believe, times where I tell you to memorize something in this class. You need to have these 6 functions memorized. You need to know their shapes. You need to know which shape goes with which function. And you need to know what the 3 key points are on each of these functions. Very, very important. Because what I'm going to do is give you a version of one of these functions, and you're going to be asked to graph it, which means you're going to identify all the translations of how x changes and how y changes, and then draw the correct shape to connect the correct points. So let's take a look at a few examples where we're going to do just that. We're going to be asked to graph each of these functions. Let's start with y equals 1/2 x plus 3. What type of function is this? Well, we could do the y equals mx plus b and graph it that way, but to kind of set up the other problems that are coming, I want to notice that the variable, what's happening to the variable, the x, is it's just standing alone. It's just an x. That is a linear function, an x just standing alone. And so we're going to rewrite this function with f of x representing that x portion. And then build around it, it's 1/2 times that plus 3. Y equals 1/2 times the main function, the x, plus 3. And what we know then is the x-coordinate is affected by what's inside the function. And that's just x, so x equals x prime. And the new y-coordinates are affected by all the outside stuff. I should do this in a different color, actually. Let's do it in orange. The new y's are all the outside stuff. The 1/2 times the function plus the 3. 1/2 times the function plus the 3. And that gives us the new y prime. So we know the function, the linear function, has 3 key points: -1, -1, 0, 0, and 1, 1. Using these formulas that we just found to translate, our x's we found are going to stay the same. So x is at -1, 0, and 1. The y's, we're going to take half of it and add 3. Maybe even get a common denominator here by multiplying by 2 over 2. So that's going to be 6. Y plus 6 divided by 2. So -1 plus 6 is 5 over 2. 0 plus 6 is 6 over 2, which reduces to 3. And 1 plus 6 is 7 over 2, which reduces to 3. We've now got our new points for our graph. The points on our graph are -1, 5/2, 0, 3, and 1. Whoops, that's not 0, 3, that's 0, 2. And 1 7/2. And so when we connect the dots, we end up with this line. There is my linear function. So it feels very much like what we did yesterday, except that yesterday we were given a graph with points. Here we need to know what the graph, the points, and the shape are. So let's do one that's a little more exciting than a line, because really a line we could do easier as y equals mx plus b. So let's do y equals -2 absolute value of 3x plus 1 minus 4. And this time what you'll notice is the main operation here is the absolute value. That absolute value is going to be our function. What is inside the absolute value is inside the function. What is outside the absolute value, the -2 minus 4, is outside of the function. So this is how we've converted the original equation into the function notation so we could see how things are going to move with this absolute value function. The stuff inside the function is going to affect the x. X equals 3x prime plus 1. And when we solve for x prime, we have to subtract 1 and divide by 3. So that's what's happening to the x's. What's happening to the y's is outside the function, where the function becomes y. So it's y prime equals -2 times the function, or times the y, minus 4. With the absolute value, that was number 2 up above here, the key points are -1, 1, 0, 0, and 1, 1. We're going to attach them with a V shape. So the key points that we need to see how they're changing, -1, +1, 0, 0, and 1, 1. They're each going to change. The x's, we're going to subtract 1 and divide by 3. So -1 minus 1 is -2 thirds. 0 minus 1 is -1 thirds. And 1 minus 1 is 0 thirds, or just 0. The y-coordinate then, multiplying by -2 and subtracting 4. 1 times -2 is -2, minus 4 is -6. 0 times -2 is 0, minus 4 is -4. And 1 times -2 is -2, minus 4 is -6. So we now know what our graph is going to look like. And actually, I'm going to make my x's a little bit wider because we're going to be dealing with thirds inside those x's, aren't we? So the first point is at -2 thirds, -6. The next point is at -1 third, -4. And the next point is 0, -6. And if we connect the dots with that V shape that we're expecting, we get our graph of our absolute value. Let's try another example. We need to be really good at this process. Number 3, we're going to say y equals parentheses 1/3 x minus 1 squared plus 2. What's the main operation of this function? Well, as you might expect, putting stuff in parentheses and squaring it is the main operation. This is a quadratic function. So, we're going to have the quadratic function. F represents the quadratic, and everything inside the quadratic goes inside f. 1/3 x minus 1. The stuff outside of it stays outside of it, which is just a plus 2. So we have y equals f of 1/3 x minus 1 plus 2. Something that kind of bothers students is we didn't write the squared down anywhere. The function itself, we're going to let represent the squared part. The function means we square whatever's inside the parentheses. So the function takes care of the square. We don't need to write it because we've written that f to represent the quadratic function. Might even help to write the shape. This is x squared. We know what it's going to look like. So again, the stuff inside the function is going to affect the x. X is 1/3 x prime minus 1. Again, with x we have to solve it, so we're going to add 1 and then get rid of the fraction by multiplying everything by 3. That gives us our new x values. To get our new y values, we look at everything outside the function, where the function becomes y, and then there's just this plus 2. So y's are simple. The function is just added to. With the quadratic, our key points we should know are -1, 1, 0, 0, and 1, 1. So let's see what this gives us for our new points. With the x's, we're going to add 1 and multiply by 3. So -1 plus 1 is 0 times 3 is 0. 0 plus 1 is 1 times 3 is 3. And 1 plus 1 is 2 times 3 is 6. For the y's, we're just going to add 2. 1 plus 2 is 3. 0 plus 2 is 2. And 1 plus 2 is 3. We now have our new points for our graph. So if we plot 0, 3, 3, 2, and 6, 3. 3 is a little higher, isn't it? And then we connect the dots in a U shape. We see it's very wide and very fat, but we get our parabola shape. Let's try another one. Example 4. Y is equal to 2/3 times x plus 3 cubed minus 1. The main function here, you see the main stuff is cubed. That is our main function. It is a cubic function, which we know looks something like that. So we're going to make f represent the cubed part. And inside the cubed part is the x plus 3. Outside of the cubed part is the 2/3 times the function minus 1. This then becomes the function we're going to translate, transform, and move. As usual, the stuff inside the function is how x is going to be changed. X is equal to x prime plus 3. And we always have to solve the x, so we'll subtract 3 from both sides. So we're going to subtract 3 from all of our x coordinates. The the y's, we take the outside stuff where the function is y. So y prime is 2/3 times the function y minus 1. And again, we might want to get a common denominator by multiplying by 3/3. So y prime is 2y minus 3 divided by 3. On the cubic, our key points, again, you're going to want to have these memorized. Number 4 here, the cubic, the key points are -1, -1, 0, 0, and 1, 1. So -1, -1, 0, 0, and 1, 1. The x's are easy to transform. Here we're just subtracting 3. -1 minus 3 is -4. 0 minus 3 is -3. And 1 minus 3 is -2. The y's, we're going to multiply by 2, subtract 3, and divide by 3 in that order. So -1 times 2 is -2 minus 3 is -5/3. 0 times 2 is 0 minus 3 is -3/3, which reduces to -1. 2 times 1 is 2 minus 3 is -1/3. And we have our 3 key points. So let's graph it. We need to go thirds going up, so I'm going to make my going up a little bit bigger and going down a little bit bigger so that we can identify where those thirds are. So the first point is at -4, -5/3. Our second point's at -3, -1. And the next point's at -2, -1/3. Oops, -2, -1/3. And then we connect it using our shape. It's going to come up, come through, level off, and then come back up. Maybe not quite that shallow, or that steep, but it'll work. We have the graph now of 2/3 times x plus 3 cubed minus 1. Let's try another example. This example is going to be y equals 1 over 3x minus 5 plus 2. The main graph, the main function here is 1 divided by the stuff. It's a reciprocal function. Remember, the reciprocal function is going to have the asymptotes. So the reciprocal function is going to represent the f. Whatever's inside the reciprocal goes inside the function, the 3x minus 5. Whatever's outside the reciprocal, plus 2, goes outside the function. And so again, we can figure out what's happening to our x's and what's happening to our y's. X is equal to 3x prime minus 5. Solving for the x prime, we have to add 5 and divide by 3. And that's our x function. Our y function is whatever's outside. We place in the function with y. We've got y prime equals y plus 2. That one's going to be really simple. And then we're ready to look at our 3 key points. -1, -1, 0, 0, and 1, 1. Remember, 0, 0 on the reciprocal function is the intersection of the asymptotes. It's not part of the graph. It's where the asymptotes cross. Okay, so to get our new x's, we're going to add 5 and divide by 3. So negative 1 plus 5 is 4 thirds. 0 plus 5 is 5 thirds. And 1 plus 5 is 6 thirds, which reduces to 2. With the y's, we're just adding 2. Negative 1 plus 2 is 1. 0 plus 2 is 2. And 1 plus 2 is 3. We've got now our 3 new points. On the x's, we're going to want thirds, so I'm going to go a little bit big so we can identify where those thirds are. So plotting our points, 4 thirds, 3 4/3, comma 1. It's supposed to be pink. There we go. 5 thirds, comma 2, and 2, comma 3. Now remember, those points are not all on the graph. The center one is the intersection of the asymptotes. So go ahead and draw your asymptotes that have a crosshair at that center point, and then you can graph around the asymptotes. That last one wasn't very good. Our reciprocal function. One last function type we haven't seen yet. Let's do one more example. We're going to do y equals 2 over 3x plus 1 squared minus 4. And what you see here is the major function occurring is we're dividing by stuff squared. This is the inverse square function. Remember, the inverse square function had the same asymptotes, but it was top left and top right. So if the function represents the inverse square, what's inside the inverse square goes inside the function, 3x plus 1. What's outside the inverse square, which includes the multiplying by 2 on top, because there used to be a 1, right? The inverse square is 1. So this fraction is actually saying 2 times 1 over the inverse square. So we need to multiply that 2 times the function and subtract 4, and that, in function notation, is what we're dealing with. Again, the stuff inside the function affects how the x is going to change. X is 3x prime plus 1. So solving, we have to subtract 1 and divide by 3. That's equal to x prime. Again, the y's are what happens outside, where y is the function. So y prime equals 2y minus 4. And now we just have to shift those 3 key points. And on the inverse square, again, you're going to want to memorize these. Negative 1, 1, 0, 0, and 1, 1. And let's see what we end up with for our new points. For the x's, we subtract 1 and divide by 3. Negative 1 minus 1 is negative 2 thirds. 0 minus 1 is negative 1 third. And 1 minus 1 is 0 thirds, or just 0. For the y's, we multiply by 2 and subtract 4. 2 times 1 is 2, minus 4 is negative 2. 0 times 2 minus 4 is negative 4. And again, 1 times 2 is 2, minus 4 is negative 2. And so now we have all the points we need. I'm going to make a really big 1, 2, so that we can see all those thirds in there. Not really to scale, but we'll get the point of what the graph looks like. The first point's at negative 2/3, negative 2. The second point's at negative 1/3, negative 4. And the third point is at 0, negative 2. Again, remember with the inverse or the inverse square, there is an asymptote through the center points. It's where the two asymptotes are going to cross each other. So now we can, whoops, that's the wrong color. Now we can connect those other two dots going through those points and bending. We now have the graph of the inverse square. So that's just a quick example of each of the different types of graphs going through the same process that we went through yesterday. The biggest difference is you need to have these 6 graphs memorized so you know how they behave, what their shape is, any asymptotes, and what the key points are. I want to wrap up though by looking at one other thing. We're not going to spend a lot of time on it, but it's good to be exposed to it, is what happens when we take the absolute value of functions. Absolute value makes things positive, right? So first we will graph what is inside the absolute value then we will make the negative positive. And remember, that means anything that's below the x-axis moves above. That's taking the absolute value, making everything that's negative positive. Then we will graph whatever happens outside the absolute value. So let's just do 2 quick examples of this process so you can see how it works. Let's start with a really simple one that just has an absolute value of x squared minus 4. We'll first look inside the absolute value, and what we see is happening is we're squaring inside the absolute value. That squaring we know is a parabola, and we're subtracting 4 from that function, which is nice because nothing really happens to the x. X is still the same. And really the y's are just as simple because we make y equal to the function. And we subtract 4, and that's going to be equal to our new y's. With the quadratic, the key points are negative 1, 1, 0, 0, and 1, 1. We said we were going to keep the x's the same, x equals x prime, so negative 1, 0, and 1. The y's we said we were going to subtract 4 from. 1 minus 4 is negative 3, 0 minus 4 is negative 4, and 1 minus 4 is negative 3. So then we draw our preliminary graph that reflects these points. Negative 1, negative 3. 1, 0, negative 4, and 1, negative 3. And then we draw our graph. That's the preliminary graph. Because now what we need to look at is we're going to do the absolute value bit. The absolute value is going to take the part that was below the x-axis, and it is going to reflect it up above the x-axis. Oops, I want black. So, we have this point down here at the bottom of 0, -4. That's going to reflect up, making the y positive. 0, +4. We have this point at 1, -3. That's going to reflect up, making the 3 positive, giving us 1, 3. The -1, -3. -1's the x-coordinate. Don't change the x. We take the absolute value to change the y-coordinate to now a +3. And we see that the graph, didn't mean to make that disappear. I don't even know how I made that disappear. I can't make it come back. We see the graph, that green highlighted graph, bends down all the way to about 2. Bends down all the way to about 2. The 2 wings on the outside were already positive, so those are going to stay exactly the same like they were before. And so you can see what we've done is we've taken the green part that was below the x-axis and flipped it up above the x-axis, making it positive. That's what absolute value is going to do. Flip it up positive. Let's do one more example before we wrap up today. Let's do y equals 2 absolute value of x cubed plus 1 minus 1. Again, we're going to start by looking inside the absolute value. And the function inside the absolute value is a cubic. Cubic shaped like this. That's going to be my function, and we're adding 1 to it. Which is nice because the x's don't change. X equals x prime. The y prime, that's what happens outside of the function, outside of the y, which means we add 1. Y plus 1. So the key points are -1, -1, 0, 0, and 1, 1. The x's, we said, were all going to stay the same, so -1, 0, and 1. The y's, we're going to add 1 to them. -1 plus 1 is 0, 0 plus 1 is 1, 1 plus 1 is 2. And so when we graph the original cubic, what's inside the absolute value, we have these points of -1, 0, 0, 1, and 1, 2. So the graph comes up and bends. We now will take the absolute value, meaning the part that's below the x-axis has to reflect up above. Since we don't really have any points, we're just going to take the shape. All the points we had were either on the x-axis or above, so those points were all good. But the part that's below is going to bend up above. Although we still haven't done the multiplying by 2 and subtracting 1 on the outside. Those are all affecting the y-coordinate. It's going to be moving us up and down and stretching us. Essentially what we have is a new y rule. Y prime is equal to 2y minus 1. So we're going to take the points that we had before and apply this new y rule. So the points were negative 1, 0, 0, 1, and 1, 2, and now these points are going to shift again. The x's staying the same of negative 1, 0, and 1. The y's now have this extra step. Multiply by 2 and subtract 1. So 0 times 2 is 0, minus 1 is negative 1. 1 times 2 is 2, minus 1 is 1. And 2 times 2 is 4, minus 1 is 3. So now we've got our new key points, and the graph above is going to be our guide for the shape around the key points. So the key points are negative 1, negative 1, 0, 1. Again, not sure why my axis likes to disappear. And 1, 3. And I can see looking above that if I start at the left point, it looks like a cubic. That doesn't look like a cubic. Come up, level off, come up. But then from that left point, it goes up. And so again, I've used the shape above and my new translated points to end up with my final solution for the absolute value graph. What's nice about today's lesson is once you take a look at and master the 6 functions that we started with, learn their key points, learn their shape, learn their behavior, then everything we do today looks a lot like what we did yesterday. So take a look at the homework assignment, practice a few before you come to class to get the feel of moving these, and we will see you in class with any questions.